Imagine you're an intrepid space explorer. You decide to write down all your amazing discoveries, your favorite memories, your secret recipe for cosmic chili, everything that makes you, well, you. You seal this information in a bottle, and toss it into the grandest, most mysterious ocean of all. A black hole. What happens to your message? Does it simply vanish, erased from the universe forever? Or does the cosmos have a way of remembering? This isn't just a whimsical thought experiment. It's a question that has pushed the brilliant minds of science to the very edge of what we know. It forces us to confront the deepest rules of reality, and ask whether the universe keeps a perfect record of everything that has ever happened. In our everyday lives, information seems fragile. A book can burn, a hard drive can be wiped, but in the realm of physics, information is considered fundamental and indestructible. Think of it like a cosmic conservation law. As vital as the law that energy can neither be created nor destroyed, every particle, every interaction, every bit of data that describes the state of the universe is thought to be preserved in some form, forever. So, when we consider your journey into the abyss of a black hole, we face a genuine cosmic dilemma. The fate of your postcard is tied to one of the greatest unsolved mysteries in all of science. To understand this cosmic puzzle, we first need to get acquainted with the culprit, the black hole. Picture a region of space-time where gravity is so colossally powerful that nothing can escape its grasp. Not a spaceship, not a planet, not even light, the fastest thing in the universe. This is the world described by Albert Einstein's theory of general relativity. Einstein showed us that massive objects warp the fabric of space-time, like a bowling ball on a trampoline. A black hole is what you get when you concentrate an immense amount of mass into an incredibly tiny space, creating a warp so deep it's more like a bottomless pit. This is the universe's ultimate prison. The boundary of this prison is called the event horizon. It's not a physical wall you could touch, but rather a point of no return. Once you cross it, all paths in space-time lead in only one direction, inward, toward the crushing center known as the singularity. According to Einstein's theory, anything that falls past the event horizon is trapped forever. Its mass is added to the black hole, its shape, its composition, its history. From the outside, all black holes look the same, distinguished only by their mass, their spin, their electric charge. It's a cosmic clean slate. But here's where another giant of physics enters the scene, and things get weird. The laws of quantum mechanics, which govern the universe on the smallest scales, have a very different story to tell. A core principle of the quantum world is that information can never, ever be truly destroyed. You can scramble it, you can hide it, you can make it incredibly difficult to read, but you can't erase it from existence. This fragile piece was shattered in the 1970s by Stephen Hawking. He studied the strange behavior of particles near the event horizon. By mixing quantum mechanics with black hole physics, he made a startling discovery. Quantum effects mean black holes are not completely black. They should glow, faintly, emitting a steady stream of radiation. This Hawking radiation meant black holes could leak. Over immense periods of time, longer than the age of the universe for big black holes, that slow leak makes the black hole lose mass. After unimaginable time, it evaporates completely, vanishing in a final puff of radiation. The ultimate prisons of the cosmos have a finite lifespan, and then the contradiction became a crisis. This is the black hole information paradox. If a black hole evaporates and disappears, what happens to all the information it swallowed? One of the most straightforward yet deeply troubling possibilities was that Hawking himself was right in his initial conclusion. Perhaps the information is simply destroyed. In this scenario, when the black hole evaporates, it emits purely thermal radiation, a random, featureless glow that contains no trace of the unique objects that fell inside. This idea, however, sent shivers down the spines of most physicists. So, what if the information isn't destroyed? What if it somehow escapes? The most obvious escape route would be the Hawking radiation itself. Perhaps the radiation isn't perfectly random and thermal after all. Maybe in some incredibly subtle way, it's encoded with the information of everything that ever fell into the black hole. The information wouldn't be lost, just scrambled into a new form, like burning a book, and then trying to reconstruct the words from the smoke and ash. This led to one of the most mind-bending ideas in modern science, the holographic principle, proposed by Gerard T. Hooft and later developed by Leonard Susskind. This principle suggests that the information about what falls into a black hole never actually makes it inside. Instead, it gets imprinted, encoded on the surface of the event horizon, like a two-dimensional hologram that describes a three-dimensional object. Think of it like this. The event horizon acts as a cosmic hard drive, but if the holographic principle is right, they would hit a firewall of high-energy particles at the horizon that would incinerate them instantly. The search for a solution has opened a Pandora's box of speculative physics. Some theories propose that black holes don't evaporate completely. Others suggest that the information escapes into a baby universe that buds off from our own. Perhaps the singularity at the center of a black hole is actually a gateway, a wormhole, that connects to another part of our universe or another universe entirely. The possibilities are as vast and wild as the cosmos itself. After decades of brilliant minds wrestling with this cosmic conundrum, where do we stand today? The simple answer is, we still don't know. The black hole information paradox remains one of the biggest, most fundamental unsolved mysteries in physics. Each proposed solution seems to trade one problem for another. Escape of scrambled information in Hawking radiation holographic surfaces baby universes. Solving the paradox isn't as simple as picking the most appealing story. Any valid answer must perfectly reconcile the ironclad laws of quantum mechanics with the unyielding geometry of general relativity. The debate continues to rage in the halls of academia and at scientific conferences around the world. Physicists are divided into different camps, defending their preferred solution with complex mathematics and thought experiments. Some are convinced subtle correlations in Hawking radiation hold the key. Others are all in on the holographic principle, believing it points toward a revolutionary new understanding of gravity and space itself. The lack of a clear answer isn't a sign of failure. It's a sign we're probing the absolute limits of our knowledge. This mystery is so compelling because the stakes are so high. It's a direct confrontation between the two pillars of modern physics. Both theories have been tested to incredible precision in their domains. But in a black hole, their rules clash, and one or both must be incomplete. In the end, the quest to solve the black hole information paradox is part of a much grander human endeavor. The search for a unified theory of everything. Physicists dream of a single, elegant framework that can describe all the forces of nature, from the fall of an apple to the dance of subatomic particles to the birth of the universe itself. They are searching for a theory of everything, sometimes called quantum gravity, that would sing one universal song, explaining all of cosmic reality with a single set of principles. The information paradox is a signpost, pointing directly at the territory where such a theory must live. This grand quest is what drives us to build massive particle accelerators, to launch powerful space telescopes, and to fill blackboards with equations that stretch the limits of human imagination. We are explorers, and this paradox marks a giant "here be dragons" on our map of the cosmos. It tells us that beyond the known world of relativity and quantum mechanics lies a new frontier of discovery, a deeper reality waiting to be uncovered. Solving it would likely rewrite our understanding of space-time, information, and the very origin of the universe. It's a challenge worthy of our species. The universe is under no obligation to make sense to us, but the fact that it does, at least in part, is the most wonderful thing. We have found a deep and beautiful order in the cosmos. The black hole information paradox is a reminder that there is still so much more order to find, so much more beauty to reveal.